We often make careful measurements of the same thing on different occasions, but it's rare that we get the same value for our measurement on each of these occasions. It could be because our measurements are taken on samples, and different samples result in different values. Or it could be because our measurement process is only an approximation for what we're trying to capture. Statistical methodology is developed to allow us to learn from these kinds of noisy measurements. And in order to do this, we need mathematical models for the randomness in this noise. So in order to understand statistics, we're going to need to understand some probability. Probability is what makes statistical methods work. Probability models give us mathematical ways to describe how the randomness in our data occurs and allows us to describe the variability that we get in our data. Random outcomes can occur in a number of ways. Here's some examples. Samples differ from the populations from which they were randomly drawn, and they differ from one random sample to another drawn from the same population. We'll want to be able to quantify this randomness. Some measurements are imperfect, and the error in the measurements is typically modeled as random noise. And in experiments, probability allows us to model how the random assignment of subjects to treatments explains the variation between treatment groups that is due to chance, so that we can understand the variation that can be attributed to the different treatments. We use probability to quantify the uncertainty of some random circumstance. Sometimes we call this a random experiment, that is, a process with a random outcome. The probability models for some random experiments are well known. Here, we'll flip a typical coin 10 times. The coin is heads on one side and tails on the other, and the chance that heads or tails comes up when we flip it is 50-50. That is, the probability of each one, heads or tails, is 1/2. But now suppose we flip the coin 10 times. That doesn't mean we'll get exactly 5 heads every time we do that. Let's flip the coin now and see what we get. We got 6 heads in our 10 flips. But if we did this again, we might get 4 or 5, maybe 7, even possibly 0 or 10 heads, although these extreme values are less likely. Sometimes we perform random experiments without having background knowledge of the outcome we expect, like we did when we flipped the coin. So instead of flipping a coin, let's now flip a beer cap. This beer cap is red on one side and silver on the other. A beer cap has an irregular shape, so that means we don't know which side is more likely to come up, red or silver, and how much more likely it is. We'll flip the beer cap 10 times. We got 4 reds and 6 silvers. We can use the outcome of this experiment to estimate a probability model for the probability of getting red when we flip the beer cap. We got 4 reds in 10 flips, so we could estimate the probability of getting a red as 0.4, 4/10. But are you convinced that it really is 4/10? These are the types of statistical questions that we need probability to help us answer. Some examples of other processes with random outcomes are the number of reds we get when we flip a beer cap 10 times, the birth weight of the next baby born in a hospital, or the number of babies born at the hospital that day that are boys, or how long we need to wait at a bus stop until the next bus arrives. The outcome of these random processes can all be described by a numerical random quantity, which we'll call a random variable. A random variable takes an outcome from a random experiment and gives it a numerical value. Typically, random variables are denoted by uppercase letters later in the alphabet. So as an example, we'll let V be the number of reds we get when we flip a beer cap 10 times, W be the birth weight of the next baby born in the hospital, X the number of boys born at the hospital that day, and we'll let Y be the wait time for the next bus. Suppose now we want to consider the probabilities associated with these random variables. We're considering the probability that they could take on certain values. Suppose, for example, we're interested in the probability that we need to wait more than 5 minutes for the next bus. We'd write this as the probability that Y, our random variable for the wait time for the next bus, is greater than 5. To be a valid probability, the probability that Y is greater than 5 must be a number between 0 and 1. If it has probability 1, it is sure to occur, and if it has probability 0, it is sure not to occur. Suppose the bus arrives in 5 or fewer minutes. The probability of this, the probability that Y is less than or equal to 5, is equal to 1 minus the probability that Y is greater than 5. In general, the probability that something does not happen is 1 minus the probability that it does happen. Random variables are independent if knowing the value of one provides no useful information about the value of the other, or technically speaking, it does not affect the probability of the other random variable. As an example, 2 rolls of a die are independent. If we got 1 on one roll, that does not mean that we are more or less likely to get 1 or any other number on the next roll. But for an example of random variables that aren't independent, suppose we know the birth weight of a baby. Well, that might give us some information about whether that baby is a boy or a girl, because on average, boys tend to be a little larger than newborn girls. So for example, if we know the baby is large, it's more likely that the baby is a boy rather than a girl. So if we have sex as a random variable, say we're counting it as 0 for boys and 1 for girls, then birth weight and sex of a newborn baby are not independent random variables. Random variables can be discrete or continuous. Here's what those are. A discrete random variable can take one of a countable list of distinct values. In other words, we could make a list of the possible values that the random variable could be. Examples of discrete random variables include the number of times the red side is up when we flip a beer cap 10 times. Another example is the number we get when we roll a die. And a third example could be the number of people in line when you arrive at the coffee shop for your morning coffee. A continuous random variable can take any value in an interval or a collection of intervals. The key to understanding a continuous random variable is that we can't write down every possible value it could be, at least not to any number of decimal places, although we could write down the range of values it could be. Examples of continuous random variables are birth weights of babies and the wait time for the next bus. We'll need to be able to distinguish between situations where our measurements can be thought of as discrete or continuous so that we can choose an appropriate probability model. In order to make conclusions from data, we need to understand how our data, which were observed in the real world, relate to our probability model, which is a theoretical world version of how our measurements behave. Our next step is to learn more about some commonly used probability models.